You might remember from your study of introductory calculus about ideas of minimums and maximums. And if you go all the way back to the initial study of calculus, you recall you can think of a minimum as a point where any point around it has to be smaller, so it's just kind of a peak, and there's kind of a valley for a minimum, peak for maximum, valley for minimum. And we have similar concepts when we think of functions in multiple variables. You kind of look over here, and it's pretty clear that the top of this bell shape is a maximum. But in this particular case, you don't have a single point of a minimum. What you have is this whole little ring, this whole little surface, and all of those points are at the minimum point because all around there, they're all at the bottom value of the function. So let's develop some more rigorous language to talk about that. When we say that we have some function f of two variables, and it's defined on some domain D, right? So just all the different values that can go into it. If we take a slice of that domain S, so common things might be just for positive values of x and y, for instance, or maybe positive ones for x, but all the values that you could have for y. For instance, we say that the function f has a minimum at some point AB if all the other points, when they're evaluated, are no smaller. So they're at least as big and often larger than the function at that point. We call that a minimum. And that makes logical sense, right? All the points of this bell here are, there's the floor of it, and then there's points that are larger. So all these points make a minimum. And similarly, we have a maximum at this point if all the points in that little subset are less than or equal to this. So they're all smaller or no larger at least. And the same, that's true here. I have a single point and every function value has a z value lower than that top purple point. Now, if we're talking about, instead of saying some subset, instead of saying just the positive values or just the negative values or something like that, if we consider the whole domain of the function, then these points can be called a global or absolute minimum or global or absolute maximum. So the terminology is simply to say it's a minimum when we're thinking about a constrained piece of the domain, but it's a global. I believe the term, sometimes you'll hear this term as local minimum and local maximum. And when we're talking about this here, we usually use the term relative. But anyway, so the idea is if you're talking about the whole domain of the function, that's when we really talk about global functions, or global maxima and minima. Now there's a specific result here, and the proof's a little beyond what we want to discuss in this class, but if the subset is closed and bounded, so closed means it includes all of its boundary points, so it's not an open set, it's a closed set. And bounded just means that it's finite, like it doesn't go off to infinity, for instance. So if it's closed and bounded and the function's continuous, then it's got to have at least one minimum and one maximum. And you think about that makes complete logical sense. If I think about some space and I have a continuous function, right, so it's always through, there's some point in that function that's the highest value and the lowest value. If the function is discontinuous, everything goes out the window. But for a continuous function, on some closed bounded set, there's got to be an upper limit and there's got to be a lower limit. And finally, we call maxima and minima extrema. So those are just other words for the same thing. But I want to use that to talk a little bit about these two diagrams here. So what we notice in this particular case is that I have one single maximum. And I don't know, in this case, I haven't determined whether or not I'm just talking about some subset or the domain, but that's a maximum because clearly everything is less than or equal to that. But this whole little ring on the bottom is a minimum. It's a minimum because all those points are equal to each other, and all the other points are larger than that. So each point in there is a minimum, so they're all minima. But over here we have a slightly more interesting case. We have something that kind of looks like a sine wave, but it dips a little bit and then peaks a little bit over here. So what you have on these peaks, and this one as well, is what's called a relative maximum. So around that point, everything else is smaller. But if you look at the whole function, it's not the highest point on the function. It's just the highest point in its little region. Whereas this is the truly highest point of the function. Similarly, this is the lowest point of the function totally, but these points over here are still smaller than every point around them. And that's the idea of what I want to talk to here. We say that f has a relative or local minimum at AB if there's a small region. So if I were to take, let's take a blue marker here. If I were to take a small slice and just slice this region out and only look at the function on that slice, this would be the maximum in that slice. So I'd sliced it. And that's kind of how you define it. Technically speaking, what they do is they describe what they call an open disk. So you take the point, you kind of draw a little circle around it and you check it there, but that circle can be as small as you need it to be. So you have these relative maxima here. And similarly, you have, if you were to slice it down there, you'd have relative minima. And the idea is you have relative minima if all the function values are larger than this point, relative maximum if all the function values are smaller or equal to the point there. And realistically, it's just a natural extension of what we've discussed in introductory calculus. But it's important to start developing this because we're going to learn some techniques that are similar to what we did in introductory calculus to find values when we have a function explicitly given.